Okay, we are on to chapter 10, and so last time we got into chapter 10 a little bit, and we started talking really about sort of solubility with solutions, and the idea of really sort of like dissolves like. And it's really the idea of, as we talked about, that the way things are able to interact with other molecules, for example, they will definitely be soluble. They definitely will be able to mix together if they're both using basically the same type of intermolecular forces. So really this all revolves around sort of those intermolecular forces we talked about. So when different substances come in contact with each other, if they're really using the same type of intermolecular force that they use really with themselves, they're able to really interact really well together. So again, a majority of those guys is going to be either hydrogen bonding, it's going to be dipole-dipole interaction, or some type of dispersion force. And really what that leads to is things that are typically polar and polar are going to be soluble in each other and will mix. Things that are ionic and polar will also be soluble because they could do ion dipole interaction. Things that are nonpolar and nonpolar are able to be soluble in each other. So all these guys, should be soluble in each other. While, the most part, if you sort of cross over, you're going to get somebody that's nonpolar and polar together. Again, they will usually be insoluble in each other. And that's because, for the most part, the difference in the way that they can interact with one another is very different. Again, the nonpolar guy is probably going to be using dispersion forces, which are those weak temporary type of forces, while the polar guy is going to try to use either hydrogen bonding or dipole-dipole sort of interaction. Again, they could sort of interact with one another for sort of the short period, but over sort of the long haul there's really no way to maintain that interaction. That's because polar molecules are pretty much locked into their polarity. What I mean by that is they always have a separation of charge here. So they're always a positive and negative guy together, side of the molecule. That never changes. So they're always ready to interact in that way. Nonpolar guys, again, need something to sort of happen to help them get that sort of charge, and they're not going to be able to maintain it over a long period of time. We also talked about sort of different ways to classify solutions. There's saturated, which means that basically the maximum amount of solute has been dissolved. So at a particular temperature, remember solubility, especially with solid and sort of a liquid, is based on temperature. At a specific temperature, there is a maximum amount of solute that you can get to dissolve. And if you hit that sort of point where you hit all of it dissolving, that is going to be a saturated solution. An unsaturated solution is one where you obviously have not hit that yet. So you have not hit the max. So in an unsaturated solution, you can continue to dissolve more solute. It will continue to dissolve until really it does hit this saturated solution. And at that point, you really, again, will not get any more to dissolve. Any questions on any of that stuff we talked about last time? So another way, or another type of solution is what is known as a supersaturated solution. A supersaturated solution is one that contains really way too much solute that is there for that amount of solvent. So it is still a solution at a point, but it creates a lot of times a very unstable sort of solution. So for example, one way you can make a supersaturated solution, which is an experiment they used to do years ago, you take something like, say, sodium acetate, and you basically would heat it up and you would put a lot of sodium acetate in there, and that would allow it all to basically dissolve. And because you're heating it up, it's going to allow really a lot more solid to get there and get to dissolve than you would if you just kind of did it at room temperature. So as you heat it up, you're getting a lot more of that solid to dissolve. You're also doing a little bit of evaporation of the solvent, like water, along the way. Typically what you do after you do that, you get all that sort of solid to dissolve, is you now will be left with a solution, and you kind of let it cool, and you really don't disturb it or anything like that, and you let it cool down. Now when you do that, as it's cooling back down, what happens is the solubility of that solvent really now changes. It now is like you could only have a little less there dissolved in it. The deal, though, at this point is you've already got all that solid dissolved, so it's still a solution. And what ends up happening is at this point, when you kind of make a supersaturated solution, you end up with a solution here after it's sort of cooled back down, where you have way too much of that solid dissolved in it. But it's still, at this point, really a solution at this point. It is so unstable that if you just took, like a speck, whatever you dissolved in there, and you just kind of dropped it in, what would happen is that little speck of the solid that you put in there would be enough for it to realize that's way too much solid in here that we have dissolved. And what will happen is it will go from a solution, and you'll start to see actually all the solid start creeping out of the solution. And what will happen, it'll go from a solution to basically a rock hard solid at that point. And that will allow all the solid basically to come out of solution because you had way too much of it dissolved in there. These are so unstable. I still do this experiment at one demonstration that, if you accidentally, even before you get to dropping the thing in, the little seed of what you dissolved, if you actually bump it too hard, it will cause it to actually start to come out of solution. I've done that many times, just literally just kind of lifting it up and just putting it down very gently. That it's enough for it to realize it's not good. It has too much dissolved in it, and it will come out of solution. So supersaturated solutions, again, are solutions that basically have way too much of the solute past what should be there in terms of the saturation point. And it really is a lot of times very unstable sort of solutions. And that's this is actually the experiment. This is actually the experiment I was talking about. So this is like sodium acetate in a supersaturated solution. You can barely see it maybe, but there just did like one little drop of what was dissolved in there, and you can start to see the solid forming here, and all the solid is basically starting to come out of solution. And then at this point, it's pretty much a rock hard solid at that point. So it's a cool kind of experiment. You don't do it anymore because he used to have you put like your thermometer in there. And then at the end, you had like a lollipop because your thermometer was. All right. So let's talk a little about pressure and solubility of gases here. So the external pressure has an effect on the solubility of gases. As we talked about, the sort of higher the pressure, the smaller the volume, there's going to be a lot more solubility of the gas in the liquid component. And that's basically Henry's law. Henry's law says that the solubility of a gas in a liquid is proportional to the pressure of the gas over the solution. And there's two versions of this equation, but it's kind of the same thing. This is the concentration is equal to K times P. C is molarity. K is Henry's constant and is specific for the gas you're dealing with. So it would be a value that you would find in a table. P is the pressure there in atmospheres. Or sometimes you'll see it like this: S is equal to Kp. S here is the molar solubility, which is really molarity anyways. But sometimes people will use S to represent molar solubility is equal to that. This is sort of the soda can sort of example here. If you have a soda can, right, it's under a lot of pressure, and a lot of the CO2 is dissolved in the liquid part of the soda before you kind of pop the top. So under that pressure, all the gas is, in a smaller volume where the liquid would be, and that's what keeps it carbonated. Once you open the top there or pop the top of your can, you release all that pressure. That's going to allow all the CO2 gas molecules basically to escape, and that's like the fizzing that you see, right? That's coming out of your soda can here, and it's all that CO2 that's being released. In addition to sort of releasing the pressure, you also provided an escape route, right, for all that CO2 basically to escape. That's why if you leave a can of soda open for a while, right, and you come back to it, it tastes very flat, right, because all the CO2 basically was able to escape through the top there. And again, before you pop it, you can see a lot more of the CO2 there in the liquid part. As you release that pressure, that's going to allow them a greater volume and a chance to sort of escape the liquid part of the surface. Now, this is an example table of, again, Henry's Law's constants, which you could look up. Again, always in a table, you want to make sure you double check the units. But you can see there's some different values for different gases. So it is gas specific as to what you would look up for there. So let's take a look at one. Why don't you try it? What is the pressure of CO2 that's required to keep the carbon dioxide concentration of 0.12 molar in a soda at 25 degrees Celsius? So that's the Henry's constant there for. Okay, let's take a look. So again, our molar solubility will equal our Henry's constant times the pressure. So in this case, we are looking for the pressure, which would be the molar solubility divided by K. And since we are given the molar solubility, which is really the molarity, which is 0.12 molar, divided by our constant 3.4 times 10 to the minus 2 molar atmospheres. Here the molarities will cancel, the atmospheres go to the top when you divide it, and we will end up with here, looks like about 3.5 atmospheres. Any questions on that calculation there? 3.5 atmospheres is, about, what is that, like 3 times greater than like 1 atmosphere, which is normal pillar pressure, right? To keep that CO2 there in your soda pretty fresh. All right, so now we're going to talk about some concentration units, which we've already talked about previously when we were doing sort of titrations and stuff like that, but it is officially in this chapter, which is chapter 10. So we're just going to kind of, again, review some of these, and we did some of these examples, obviously, previously during lecture. So just a reminder, some important concentration units that we saw, which was, again, this is our percent mass to mass, which is the mass of the solute divided by the mass of the solution times 100%. And remember this one, the important part there is the bottom, which is the mass of the solution. You want to make sure, again, that you get the mass of the solute and the mass of the solvent. We also had some other ones that we talked about, which were some other percent ones, which is percent volume to volume, which is the volume of solute divided by the volume of solution times 100%. And we also had percent mass to volume we talked about, which is the mass of the solute divided by the volume of solution, also times 100% there. So these are 3 of those sort of percent concentrations, which are important sort of units. And again, we talked about as well that you can, if you do have sort of the percentage given to you, sort of turn it into a conversion factor. Reminder that if you had something, again, like 3.25% by mass, sodium bromide, that would be 3.25 grams of sodium bromide over 100 grams of solution. Our opposite of that, 100 grams of solution would be 3.25 grams of sodium bromide. So sometimes it's easier if you sort of have the percentage given to you to kind of convert it into a conversion factor, do a little dimensional analysis, and sort of solve for where it's missing. So obviously in this one, like we did previously, a solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Again, this is the solute, which is our smaller part. the water here would be our solvent. So in this case, we would do our percent mass to mass, which is our mass of our solute, mass of the solution, times 100%. So here, the important part is we want to get that mass of the solution, and we want to add it together. So that would be not a 1, that would be 2.5 grams plus 50 grams, giving us 52.5 grams of solution. So our percentage here would be 2.5 divided by 52.5 times 100%. And again, like we got previously when we did this one here, I believe 4.8% or 76%. Mass. We also saw this one here where we did have a percentage. And as I mentioned before, again, we can sort of convert that percentage into a usable sort of value here. So if this is 37.2% by mass, we could call that 37.2 grams of HCl and 100 grams of solution. And in this problem, we have 35.5 grams of solution given to us. And using a conversion factor sort of approach here, we'll do our 37.2 grams of HCl over 100 grams of solution. And in this case, I think it was like 12 point something when we did it. 13.2 looks good. 13.2 grams of HCl. A reminder that the name of the solution, as we talked about, right, is always going to be the solute. So if you have a sodium chloride solution, as we talked about, that's going to be the solute. So whatever the name of it is definitely the solute. Obviously, as well, you could have, as we talked about earlier when we went over this example, you could have just plugged it into this equation, which is basically the same math as what we just did. And obviously solve for the mass of the solute. So it would be the same. We also talked about molality earlier on, and a reminder that molality is different than molarity that we talked about. Molality, again, is little m, and it is moles per kilogram of solvent here. And that is obviously different than what we saw, and we'll see here again at molarity, which is our moles per liter. So again, those are different type of guys. So like we did here, this is obviously our solute. That is our solvent. So we would want to convert our grams into moles by taking our molar mass here. Which looks like it is about 6009 for this guy, 6009 grams per mole. So we'll get our 61.7 grams. Again, we're going to use the molar mass here to divide and get our moles of our solute. Gives us 1.027 moles. And in this case, we have 175 milliliters of water that has a density of 1 gram per milliliter. Gives us 175 grams of water. But remember that we do need it to kilograms. So that's going to divide by 1,000. Gives us 0.175 kilograms in this case, which gives us our molality of 1.027 divided by 0.175 kilograms. Gives us 5.87. And again, as we talked about, you could leave it just like molarity, you could leave it in moles per kilogram. Again, the number always stays with the moles part. It's always like 1 kilogram on the bottom, or you could just write the small m in that case as well. Any questions on that there? Summer, so we did it pretty close to just now. All right. Now, molality, is a really important sort of unit for what we're going to really talk about next, which is colligative properties. So we do see molality show up a lot in those sort of colligative properties where we'll talk about. In addition, the mole fraction will show up as well in those colligative properties. So that's, again, an important one. The mole fraction is basically like a percentage without the multiplying by 100 or multiplying by 100. So again, it is represented by the X, which is our mole fraction. And that is the moles of what you're interested in. I'll call it A, over the total moles, basically, that are there. So we do see mole fraction in some colligative properties that we will see here in a second. And obviously here, if we were doing this one, we wanted to know what is the mole fraction of methyl alcohol. So we would take the 0.328 and we want our mole fraction of this guy divided by the total moles, in this case, 0.328 plus 0.292. And that, in this case, again, like we did in previous chapter there, a couple chapters ago, gives us a mole fraction of 0.261. A reminder that you can treat this like a percentage as well, in a sense, right? We assume 100%, but in this case, since we're not multiplying by 100, we could just assume 100% would be 1. So we could subtract 1 from this number, and that would give us our mole fraction of the other component that's there. So kind of like you take 100 minus what's left there in percentages, you can take 1 minus this as well. Any questions on that there? And then obviously molarity, a very big one as well that we'll see here, some colligative properties as well. And really the most common sort of use of concentration or unit of concentration, and that is moles per liter. That's really moles of solute per liter of solution. A reminder that when we do use molarity by itself, sort of with volume, you definitely do want to make sure you convert it to liters, the volume, so everything cancels out correctly. Also a reminder that if you multiply molarity times milliliters here, you end up with millimoles, and again, not moles, so that's different. So you can multiply the molarity by milliliters, but you do get millimoles, which if you're looking for grams or something like that, you'll be off by a factor of 1,000, right? So you want to make sure that, you know, you do convert it to liters. Really the only place where it's sort of good to kind of leave it that way in milliliters is when you're doing something like the dilution equation that we also saw, which was M1V1 equals M2V2. And, you know, you can leave it in milliliters in that situation. So molarity, moles per liter, a reminder that, as we just saw again, that molality is moles per kilogram of solvent. And really the thing that sort of ties these two together, if you needed to kind of go from one to the other, is actually density. So the density is sort of the thing that sort of ties those guys together. If you kind of have to kind of cross over from going from molarity to molality or backwards there, the density is oftentimes used to do that. All right, so that was just a review of some of those concentration units that we talked about around when we did all that titration and stoichiometry, I think, and all that kind of stuff. So what we're going to now talk about, though, is what is referred to as the colligative properties of solutions. Colligative properties of solutions are properties that are really dependent on the number of particles that are present. So the number of particles that are present really affect things like freezing point, affects things like boiling points of solutions and stuff like that. So what happens, for example, you know, if we think about something like, you know, if we had a solution, just a pure solvent, and we have this pure solvent and we wanted to get to the boiling point, we would start to boil. And obviously, eventually it would reach enough pressure, those guys and those bubbles, to basically get itself to the surface. Now we have the pure solvent by itself. There's pretty much nothing kind of in its way other than essentially, you know, just the solvent there. Now, if we take something and we dissolve something into, say, our solvent. So if we take our solvent plus, say, a solute, and we kind of put some stuff in there. So now, in addition to our solvent, what we have in that solution is that blue circle, so that's some solute in there. So now there's a lot more sort of particles in the solution. And when we go to boil this, what happens is as these guys sort of gain pressure, they kind of has to contend with everything that's there. Takes a lot more sort of energy, if you will, to sort of get around and get out of solution. The result of that is it will actually increase, for example, the boiling point. So it'll take a lot more energy to allow everybody to get through there. Also, the solute may have some interactions that are happening. So to allow those guys to sort of escape the solution, there's a lot more stuff in there. And we kind of see in this case of the boiling point, we see it basically start to increase. Same thing will happen, you know, if you had sort of the solvent by itself and you wanted to freeze it, for example. If you wanted to freeze it, these guys would be able to sort of come in contact with each other a little bit easier. There's nothing really in the way. Same idea over here, though, when we do have that solute sort of dissolved in there, there's all these other particles in the way that may interact with the solvent molecules wanting to come together because we got all these other things in the way. The result of that is what we see is it will actually freeze at sort of a lower temperature. Again, these guys sort of get in the way. There's some interactions that occur. So being able to normally just sort of freeze together when there's nothing else in the sort of the solution, just the solvent, these guys sort of interrupt that natural sort of progression of everybody coming together when it freezes, everybody being able to sort of escape when it starts to boil. So there's several different types of colligative properties that we're going to talk about. The first one is going to be what is referred to as vapor pressure lowering. Now, vapor pressure lowering, the vapor pressure, if you remember, is the pressure above a liquid. And remember, at the surface of a liquid, there's always guys jumping out of solution, kind of coming back into solution. So when you have a lot of guys going into sort of the gas phase above the liquid, that's going to create a lot of gas molecules above the liquid, and that's going to result in a larger vapor pressure. So when we add a solute to the substance, its vapor pressure is lower because the molecules of the substance, they cannot evaporate from the surface as rapidly as they could when there is no solute in there. So in sort of the pure solvent, if you will, there's nothing there floating around. So they're free to sort of get up there and sort of evaporate off. The result of having some more solute particles in that with the solvent is they really kind of get in the way. And that's going to allow less of the guys to be able to escape the surface and get above into the gas phase. Since we would have less gas molecules being able to escape the solution, we're going to have a lower pressure than we would see in a normal situation when there's nothing there. This is what is sometimes referred to as Raoult's law here. And that is the vapor pressure of the component of a substance is equal to the mole fraction. So again, the X here is the mole fraction for that component, and the P with the little knot on top is the vapor pressure of the pure substance or the pure solvent by itself. So this is sort of the pure solvent. This is the vapor pressure of basically the solution, where that's not just the solvent by itself. Some other things that are happening there. The vapor pressure lowering may be defined as the vapor pressure of a substance minus the vapor pressure of the solution. That gives you the change in vapor pressure. So we would expect it to come down because of that. Once again, the idea here is these guys will now have some things in their way, if you will. So less of them are going to be able to escape. And again, less gas molecules above the liquid will lower the vapor pressure than we would see. So why don't you try one here? The vapor pressure of ethyl alcohol is 66.5 torr. Calculate the vapor pressure of ethyl alcohol in a solution that is 0.2 moles of glucose dissolved in 1.25 moles of the alcohol. Let's take a look. So in this case, we're going to calculate the vapor pressure of ethyl alcohol in a solution where we take 0.2 moles of glucose and dissolve it in the alcohol. So our glucose here is our solute, right? Our ethyl alcohol here is our solvent. It's the larger part. And when we look at glucose, glucose is really carbons, hydrogens, and oxygens. It is a non-ionic solute. or a molecular one. And what that means is when the glucose goes in, right, to dissolve, you get a glucose that comes out that's dissolved. And you basically get a one-to-one relationship in terms of what happens. So basically for every glucose molecule we throw in there, we basically get one particle that's floating around. So that one particle that's floating around for glucose, obviously more than one, but obviously for every one that we do toss in there, we have barely just one of those guys floating around, interrupting the natural process of ethyl alcohol that would normally sort of evaporate. So we could do our Raoult's law, which is our P of our ethyl alcohol here, would equal our mole fraction of our ethyl alcohol times the total pressure here, or the real pressure there of our guy. So we'll start with our mole fraction of our ethyl alcohol, and that would be the moles of the ethyl alcohol, which is 1.25, divided by our total moles, which again, we do need to add both of those guys together to get that, and that would get us 1.25 divided by 0.2 plus 1.25 gives us a mole fraction of 0.862. So that would be that. We have this given to us, which is the 66.5, the normal sort of vapor pressure of ethyl alcohol. So our ethyl alcohol here with our glucose dissolved in it would be about 86% of that, which would be 66.5 torr. You can leave it in torr. You don't have to convert it to any other unit if you don't want to. So 0.862 times 66.5 gives us about a 57.3 torr. So we do see what we were talking about in the previous slide. This is what is referred to as vapor pressure lowering. The ethyl alcohol by itself can naturally evaporate and create gas molecules above the solution that results in a pressure of 66.5. With the addition of those solute particles floating around that solution, again, going to get in the way of allowing that to naturally sort of evaporate. That's going to result in less molecules above the surface, gas molecules, and that results in the pressure going down, which is what we see here. The pressure went down to 57.3 torr. Any questions on that there? Okay. Another aspect of that's the one we just did. Another aspect that's affected by particles and sort of these colligative properties here is freezing point. So what happens in the freezing point again is all those particles get in the way of the solvent guys really coming together in their normal sort of process to freeze. The result of that is we actually see a lowering in the freezing point. It takes a lot more energy to be sort of released, if you will, to allow everybody to come together in the solid phase. And we actually see the freezing point go down from the normal solvent where it would freeze. And there is a formula here, which is the change in freezing point temperature is equal to Kf times M. So this is the change in the freezing point temperature. It is not the temperature of where it actually is freezing. So it's actually the change from the normal solvent to the temperature where the solution freezes. This is Kf. This is the freezing point constant. Now, it's really important. Freezing point constant is this. It is a value that you would find off of a table, but a lot of times people have trouble because they go to the table and they go, I can't find sodium chloride solution or something like that. And you won't. The freezing point constant is based on the solvent. So whatever the solvent is for that solution, that is what you would find on the table. So if the solvent was water, you would look up water on the table. But if the solvent wasn't water, if it was some other solution, then you would look up that solution there, or that liquid there, I guess would be the better way. So it is based off of the solvent when you look it up on that table. Again, if it's aqueous or ionic, it's going to be probably water. In a lot of cases, it will be water, but may not always be water. And our little m here is what we were just talking about and we talked about previously. That is the molality. which is our moles per kilogram of solvent. Now, when we calculate the change in the freezing point temperature, because it's a depression, that means that the solution that has obviously the solute in it will freeze at a lower temperature than the solvent by itself. So when we do that, we define the change in freezing point temperature as the temperature of the solvent minus the temperature of the solution. This is important because this will give you the correct answer in terms of like negative sign or no negative sign. Yeah. So, if you calculate, say, the change in freezing point temperature and it's like a 3 for something like water, which it normally boils at 0, that means that the change in freezing point would be 3. The temperature of the solvent normally is 0 degrees Celsius minus the temperature of the solution, which means by doing this, if we take the negative to the other side, that means our temperature of the solution will actually freeze at minus 3 degrees Celsius, not 3 degrees Celsius. So it's really important to do for freezing point, the solvent temperature where it normally freezes minus the temperature of the solution where you just calculated. And again, that will give you the correct sort of sign, if you will. So it's a very common thing that people kind of mess up the sign part of it when you do that. Any questions on that there? This formula that we're looking at here is really for sort of non-ionic solutes. So guys that are sort of molecular that will dissolve but will not create more than one ion per, or one particle per solution dissolves. We also see the same sort of effect, or a similar effect with boiling point. Once again, as I drew earlier, sort of all those guys get in the way of those guys getting to the surface and being able to naturally boil. And what we see with boiling point is it actually will cause the boiling point to elevate and go up in this case. So what will happen is when we dissolve all these particles in something like water, for example, it will cause the boiling point of water basically to increase maybe by 1, 2, 3, however many degrees. So the presence of this non-volatile solutes will cause the boiling point of the solution to be raised compared to that of the pure solvent. Antifreeze is an example of that. Antifreeze is actually an example of both things. We put antifreeze in our cars so that we do not overboil. So by adding that to your car and the water, basically, the ethyl glycol that's in there basically will cause the boiling point to go higher. So if you live in a really hot environment, your car won't overheat or overboil. It keeps it from going too high. It also does the opposite. And if you live in a cold environment, it causes the freezing point to be depressed as well. So that if you live in a really, really cold environment, it takes a lot colder of a temperature to cause all your liquids there to freeze. So it sort of lowers that down as you're doing it. It has a similar sort of equation that we see with freezing point. It is the change in the boiling point temperature is equal to KB times M. And once again, this is very similar to the freezing point one. This is not, again, the boiling point temperature, but this is the change in the boiling point temperature. This is the boiling point constant. And once again, much like the freezing point constant, it is the value that you would find on the table and obviously would be provided for you. And once again, it is based on the solvent that is used. So again, you need to find the solvent off of that table. And our little m here is, again, molality, which is our moles per kilogram of solvent here. Now, because this is boiling point elevation, this means that our solution that has the solute dissolved in it will actually boil at a higher temperature than our pure solvent. So we define the change in boiling point temperature as the temperature of the solution minus the temperature of the solvent. This, once again, is really important because it will allow you to subtract or add based on what you need to do there and not mess that up. So just to again show you, if we did a calculation and it said the change of boiling point was 5 degrees Celsius for something like water, that would give us 5 degrees Celsius is equal to the temperature of the solution, which is what we're looking for, minus the temperature of the solvent, which if it was water would be 100 degrees Celsius. That means with that subtract there, I'm going to actually add that to the other side, right? And that will give me a temperature of the solution that is 105 degrees Celsius, where it would boil versus 100 degrees Celsius. So again, these two things that I put in these boxes are really important for these calculations because, again, it's very common people will sort of subtract when they should be adding and adding when they should be subtracting. So if you keep that, obviously, in mind, you will do it correctly. Also a reminder, although water, as I mentioned, is a very common solvent for a lot of things, and we do use it for a lot of things, and you will look up the value of water in these tables for a lot of these things. They're not always, again, the solvent, and that's important for a couple of things. In addition to looking up on those tables for the values of the constants, it's also important to remember that not all substances boil at 100 degrees Celsius and sort of freeze at 0 degrees Celsius. So that is water, those two values for the temperatures. So if you happen to have a solvent that is different than water, you need to also find the proper freezing point temperature or boiling point temperature for that solvent, which the good news is it's usually in that table where you would find the kind of KF and KB values. So you usually find them in the same table, but a reminder that it won't always be 0 to 100 if it's not water. Any questions on that there? All right, so here is that table, RA table. And again, you can see what we see here, things like benzene, carbon tetrachloride, chloroform. These would all be things that are good for non-polar sort of things, solutes. We have ethanol, diethyl ether, water, for example. So water is a very common one. So these numbers you will see a lot. That is the freezing point one, the 1.86. The units are degrees Celsius divided by molality. And the boiling point is 0.512, which is our degrees Celsius over molality for the boiling point. And again, you can see the numbers there for the freezing point and boiling point temperatures. But as I mentioned earlier, again, if you were doing something like benzene, these would be the numbers you would want to use for either freezing or boiling point. And again, that would be the normal freezing point and the normal boiling point, which is again very different than 0 and 100 that you find for water. So keep that in mind as well. So why don't we try one? Okay, let's take a look. So we're doing freezing point, obviously. So we'll roll with our change in freezing point formula, which is Kf times the molality. We obviously have the molality given to us. So let's check. It says aqueous, which is sort of a key word to know that perhaps water is a solvent here. It obviously doesn't mention anything else. So it's probably safe to assume that the water is a solvent. Which is why when we would go to the table, we would look up again the Kf here for water. And really at this point, that's all we need here. So we'll put it in here. The change in freezing point temperature would be our Kf from the table times our molality, which actually was given to us. Again, if it wasn't given to you, you would then need to obviously calculate the molality using moles divided by kilograms of solvent. Here, the molality here will cancel, and that will give us 1.86 times 1.7. We'll call it a 3.2 degrees Celsius. So now this right here is not the answer. This is the change in the freezing point temperature. That is the change. So that is where our change in freezing point temperature, because it is depressed there, is the temperature of the solvent, which is water in this case, minus the temperature of the solution. Putting our numbers in here are 3.2 degrees Celsius. Our solvent, which is water, normally should freeze at 0 degrees Celsius, minus the temperature of the solution. So basically, we're going to take that negative to the other side, which means that this guy would not freeze at 0 degrees Celsius, but would freeze at minus 3.2 degrees Celsius, which is a different temperature than 3.2 degrees Celsius. If you box 3.2 degrees Celsius, your freezing point went up. It did not go down, which is not right. So again, it's really important to have that last guy there to get us to the right sort of sign. Any questions on that there? So ethylene glycol by itself, I'm sorry, water by itself would obviously freeze at 0 degrees. Adding some of the antifreeze in there basically will lower that temperature down to minus 3.2 degrees to where it will actually start to freeze. Any questions on that there? Yeah. Okay, that's what I just did. All right, so why don't you give this a try, see what you come up with. Calculate the molar mass of a compound. If a solution is made by taking 12 grams that's dissolved in 80 grams of water and it freezes at minus 1.94 degrees Celsius. So we're looking for a little bit something different here. We're looking for grams per mole. So see what you come up with on this. So since obviously water is our solvent here, we would use the KF for water again at 1.86. So take a couple minutes, see what you come up. Okay, let's take a look and see how we're doing. So we want to calculate the molar mass, which is obviously grams per mole here, of a compound who, if 12 grams of it's dissolved in 80 grams of water, freezes at minus 1.94. So obviously the 12 grams here is our solute. The water would be our solvent in this case, which once again is why we do come over here. We obviously have some freezing point information given to us, which means we should probably use our freezing point sort of equation here along the way. Now, if we think about what we ultimately want, which is the molar mass, we do have the 12 grams part of it already. So we actually have the 12 grams that we could use for our molar mass. That means what's left is we really want to maybe use the freezing point information to eventually get to moles. So if we think about our freezing point temperature equation, that's degrees Celsius, that's degrees Celsius per molality. And molality is moles per kilogram of solvent. So really the only thing that has moles in here is the molality part, which is why we would want to use our freezing point equation here to get to molality so that we can then turn it into basically moles. So that's what we're going to do. We are given that the water obviously is 0 degrees Celsius is normal freezing point temperature. In this case, the solution actually freezes at minus 1.94. So if you remember, what they gave us is not the change in freezing point temperature, but they actually gave us the temperature of the solution, which in this case would be the solvent minus the solution. So to calculate the change in freezing point temperature, the temperature of our solvent would be 0 degrees Celsius minus the temperature where this solution freezes, which is minus 1.94 degrees Celsius. We need to do this step because the negative and negative will now give us a positive number for the change in freezing point temperature, so we don't end up with any negatives where we don't want it. Now we do have the change in freezing point temperature, which is what we need for our formula here. So we could solve for molality, which would be the change in the freezing point temperature divided by the KF. And that would be 1.94 degrees Celsius, which should be positive, divided by our 1.86 degrees Celsius times molality. Degrees Celsius will cancel, molality will come up there up on top. And that will give us a molality of 1.94 divided by 1.86. And looks like 1.043 little m, which is 1.043 moles per kilogram of solvent. Any questions on that so far? Now, remember that ultimately here we're looking for moles, right? So we're close to that. We need to get rid of basically our solvent. And really the only piece of information we have not used at this point is the 80 grams of water, which is our solvent. So we do need to convert our solvent, which is our water, which is 80 grams, into kilograms. So 1,000 grams in a kilogram gives us 0.08 kilograms. We're going to take that and times it by the molality that we just calculated, which is 1.043 moles of the solute, which is what we're looking for. Kilograms of our solvent here, which is water. Kilograms will cancel. And this will give us moles of, looks like 0.08344 moles. So we're using our freezing point equation here to get to molality, which allows us to get to moles of solute, which again is the bottom part of what we need to figure out the molar mass. Now we actually have both numbers. We have the grams that was given to us, and we have the moles. So the molar mass here should be grams divided by moles, which would be 12 grams of the solute divided by 0.08344 moles. And we'll see how we did here. 12 divided by the answer gives us about 143.8 grams per mole. So as you can see here, in addition to obviously figuring out something like the freezing point of a solution, you could actually use freezing point information and also boiling point information as well to figure out something like the molar mass of what's being dissolved in that solution if you're not sure what it actually is. Any questions on any of those steps there? So again, a couple things to watch out for is really the signs. A lot of times people really screw up the signs on these calculations. The minuses and no minuses and the adding and the subtracting part of it's really important. Any questions on that? All right. So that's the one we just did. That's good. So why don't you try this one then, see how you do on this. How many grams of ethylene glycol must be added to a 1 kilogram of water to give a solution that boils at 105 degrees Celsius? Okay, let's take a look here. So we're how many grams of ethylene glycol must be added to water. So again, this would be our solute. That would be our solvent. So once again, here we would go to the table and look up, since we are dealing with boiling, the KB value, not the obviously KF value. And again, it would be for water. We also know that water normally boils right at 100 degrees Celsius, which is important as well. We want to know how many grams really of our solute. So if we think about our boiling point formula, which is not that, change in boiling point is equal to KB times M. Really, the only thing that has moles in it, once again, here is our molality, which is our moles of our solute, kilograms of solvent. So ultimately, for us to get to grams of the solute, we need to get to the moles of the solute, which means, again, we're going to need to use that boiling point information to get to the molality here. Once again, what they gave us is not the change in boiling point, but actually where the solution actually will boil with the ethylene glycol in it. That means that we need to use that relationship that we saw earlier, that the change in boiling point temperature would be the temperature of the solution minus the temperature of the pure solvent, because it elevates. So in this case, our change in boiling point would be the normal solution, or the solution here, which is 105 degrees Celsius, minus our normal boiling point of water, which would actually give us 5 degrees Celsius. So again, it's important to make sure that you get the right number there to use. You don't want to use 105 in that change in boiling point temperature. Now that we actually do have the change in boiling point temperature and we have the KB, we could use that to solve for molality, which would be the change in the boiling point temperature divided by the KB. That again gives us 5 degrees Celsius divided by 0.512 degrees Celsius molality. Once again, the Celsius will cancel out here. That will give us 5 divided by 0.512. And it'll give us something like 9.766 moles of our moles per kilogram of solvent here. In this case, we know that we have 1 kilogram of our solvent, which makes the math pretty easy. We're going to times this by 1 kilogram of water. That way the kilograms of solvent cancel, and that basically gives us 9.766 moles of our solute, which is C2. I think that's a 6H6O2. At this point, we now have the moles of our solute from our boiling point information. Last to do here is to convert it into grams by using the molar mass of that guy. So that is 2 carbons at 12.01 plus 6 hydrogens at 1.008 plus a couple of oxygens at 16. Looks like it is 6207 grams per mole times 9.766, about 606 grams of RC2H6O2 would be necessary to do that. Any questions on that calculation there? So again, the important part is this relationship here and understanding that this number, again, is the actual solution where it boils and not the change in boiling point. Any questions on that one there? So I just did. All right, so why don't we try this one here? Calculate the boiling point of a solution made by dissolving 1 gram of glycerin in 54 grams of water. Okay, let's take a look here since we're getting to the end. We're obviously once again looking at boiling point in this case, so we'll use our boiling point equation here. We have glycerin, which is our solute, smaller part, and water here, once again, is our solvent, which is why when we go to the table, we will look up the value there for water. We also know because it is water, it will boil at 100 degrees Celsius. This is normal boiling point. So we're looking for the boiling point here. So we do need to figure out the change of boiling point is what we're looking for. To help us do that, we do have the KB. We do not have the molality given to us, so we do need to calculate that. The molality here, again, is our moles of our solute, kilograms of solvent. So since this is our solute, we would need to convert that into moles to calculate that. So that'll be 1 gram of C3H8O3. Doing the molar mass from the periodic table, looks like it is 9209 grams per mole when you do that. And that will give us, looks like 0.01086 moles. We want to then divide it by the kilograms of solvent. So that is 54 grams of water, which if you divide it by 1,000 will give you 0.054 kilograms. So to find the molality, it would be 0.01086 moles divided by our grams converted into kilograms here of solvent. And that will give us a molality of divided by 0.054. Looks like 0.201 molality. Any questions on that so far? That is, again, the kind of the piece of information that we need here in our boiling point formula. So now that we have that, our change in boiling point temperature would be our KB 0.512 times the molality we just calculated. The molalities will cancel. That will give us 0.512, 0.103 degrees Celsius. A reminder that this number is not the actual boiling point, but that is the change in boiling point temperature. So once again, you need to use our relationship. Because this is boiling point temperature, the solution will boil at a higher temperature, which means we'll actually take the solution minus the solvent in this case. That means that we have 0.103 degrees Celsius is equal to the temperature of the solution, which is what we're looking for, minus 100 degrees Celsius. Bringing that to the other side there will basically give us a 100.10 degrees Celsius is the temperature at which this solution would boil. Not a tremendous difference, but it will go up by 0.1 of a degree, basically Celsius. Any questions on that particular one there? All right. Any questions on anything we talked about today here? All right, we will lay it up here for today.